So if we talk about FPGAs from an application point of view, we know that we typically want to use them because they are powerful, they are fast, they are flexible, and they can be used in a wide range of different applications. So starting from I/O operations, so some fast onboard communication, for example, functional safety, different topics, of course, in image signal processing, and nowadays also modern artificial intelligence and machine learning stuff. However, the drawback always when we talk about FPGAs is that they are restricted in the resources which they offer. On the other side, if we talk about machine learning from a mathematical or an algorithmic point of view, again, we can say we want to use them because they are powerful and flexible, and they have shown really good performance, especially in the area of image processing for a wide range of different applications. So we can use them in case of object detection, we can use them for classification, we can use them for segmentation, and also for types of image and video signal coding stuff. However, again, we have a drawback, and the drawback is that we require a lot of resources, typically when we work with machine learning methods. So what is machine learning in general? Machine learning is an application of AI that provides systems to the ability to learn and improve from experience without being explicitly programmed. So what does that mean? So let's assume we have the following example. Our task is to recognize handwritten digits, for example. And when we talk about machine learning, then we typically have two phases. So the first phase is the training phase, and the second one is the final application of the network, so the inference phase. So in training, we hopefully have a lot of training data. So typically we have so-called labeled data. So for each input image, we know the corresponding classification, for example. So for example, as an input, we have a 5 here, and our label tells us the network should recognize a 5 here in this case. So what do we do during training? We take our input image and we push it through our network. And then we look at the output of the network. And at this case, the network tells us, okay, I think I see a 6 here. And now we take the output of the network, we compare it to our label, and then we have some kind of error description. And this error is then back projected onto the network. So we try to fine tune or to adapt the network coefficients in order to get a better classification accuracy, for example. And at some point, we can stop the training. So either when we had some specific number of training iterations, or the network converges, so the coefficients themselves do not change anymore. And then we can go to inference, so to the final application, where we do not have a backward path anymore because we do not fine-tune the coefficients anymore, but we only push our images, our new images through our network, and hopefully we trained our network well in order for this case to recognize a 5 here. So now we very briefly saw two aspects. So we saw the aspect of FPGAs where we said, okay, we want to use them, but they are restricted in the resources they offer. And on the other side, we saw a very short introduction into machine learning where we also said we want to use those methods, but they are or they require a lot of resources. So our question was, how can we combine or how can we bring both worlds together? And this is a block scheme of a company internal tool we developed, which is so-called AI ecosystem. So on the left side, you see the basic scheme of this, which covers mainly all aspects related to the machine learning side. So here we can do some model definition, we can select different network types, we can do some pre-processing on the data, we can write our training scripts, we can do model pruning, so we'll have a few slides on that later on, and do the final deployment. And then we have to build the bridge to the final target application. So in this case, this is, for example, XILINX evaluation board maybe, where we have to bring the trained network structure onto the target platform in order to do the inference on the target platform at the end. And one of our key questions to answer was, how can we select or treat a network right in order to have a good performance in the end at the target platform? So how can we select or design a model structure that can be well applied on the later specific target platform? And this brings me to the rest of, or to an outline for the rest of this presentation. So we'll talk very little bit about network selection. I have a few words on network pruning. Then I will show one example workflow for XILINX emulation board, show some experimental results for one specific application, and finally at the end a short summary and outlook. So for network selection, we go into our ecosystem and start at the very left side. So there we can choose maybe from some kind of model through a specific network. And there it's important to always keep in mind what is your application. So what do you want to do? Do you want to apply it for a classification task? Do you want to apply it for object detection? Do you want to apply it for segmentation maybe? And the second important thing is to keep in mind what is your specific target application in the end. So those two aspects mainly should decide which network you choose at the beginning. And I will show later on during the experimental results an example for object detection. So there we had a kind of very easy task where we said, okay, we want to detect our company logo at different scales, different orientations, different backgrounds. And for that, we said, okay, for object detection, typically we need two networks. So there's always a so-called base network or a so-called backbone network, which extracts the features. So this is what you typically use in case of image classification, for example. And if you go to literature, then you will see a lot of different names and different network families. So starting from VGG nets over res nets, shuffle nets, squeeze nets. And what we used for our application is a so-called mobile net, which is a kind of compressed structure, very kind of small network, which is suitable for applying it for embedded systems, for example. And then on top of that, we had a second network in case of object detection, which does the localization. So this network tells us, the first network tells us what do we see, and the second network tells us where is it within the image. And there we can, for example, use YOLO networks, or what we did, so-called SSD network from the literature. Okay, so now we designed our network or selected a network structure. We did maybe some things on our input data. We defined our training scripts, and then we go to a box which we call, which is called model pruning, which is a very interesting topic. What is it? So network pruning mainly is the idea to compress a network structure while maintaining the accuracy. So typically we see, okay, we define a network and maybe it's too large. So there are too many coefficients. The amount of storage we need is too large for the embedded system we finally want to have. So we try to further compress this network structure. So the idea is to go into the structure, search, find, and delete parts of the network which are not really important for the network output. So this is the main idea of network pruning. And typically, if we delete some structures or parts of the network, we introduce or we have some kind of accuracy drop. And therefore, typically we have a three-stage approach where we say, okay, we train our network, we do the pruning, so we look for unimportant parts, we delete them, and then we need some kind of fine-tuning in order to compensate for the accuracy drop we introduced by the pruning. So this is the main idea of network pruning, and similar as for the different network types. Also for network pruning, there's not one method which you have to use. So again, if you go to literature, then you will see very different methods which do network pruning in a specific way. So you can distinguish, for example, between fine and coarse pruning, where the differentiation is if you delete only single filter coefficients or complete filters. Then the next differentiation is between soft and hard pruning. So the question is, do you allow some kind of reanimation of pruned structures? And again, as for the network selection, the pruning strategy you choose should depend on your application scenario, and it should depend on the target platform you want to use at the end. And you have to keep in mind that pruning always strongly influences your main performance criterion you have at the end. So for example, the accuracy you have, the number of parameters you need, the amount of storage you need, the inference time you have at the end, and so on. So for us, it was very important to see that we do not want to rely on some external pruning methods which are offered as some kind of black box solution, but we wanted to integrate those methods into our workflow, into our company internal workflow, into the ecosystem, to have the full control of those methods in the end. And here's just a very brief description of one method we use for pruning, which you see in the results section. So there the idea is to go into the network, and for some test images, you look at the output of some feature channels, and you always look if those filters are active or not active. And if they are not active, and almost always not active, then you say, okay, those cannot be important, and you delete them and prune them away. So this is the main idea of the so-called APOS, or average percentage of zero activations criterion. We'll see later on. Okay, so now we talked a little bit about the left side of our workflow, and the question now is, okay, what can we do with those network structures? So how can we bring those trained networks onto the target platform, which is, in this case, I will show one example workflow for a XILINX evaluation board. And there you see, this is some kind of really complex workflow you have to work with at that point. So just a few words on that without going into detail. So what we see here at the bottom left side is our ecosystem. So here we are able to create the model, we are able to train, we are able to deploy the model, and then we finally end up with a so-called frozen graph, which is a network, a TensorFlow internal network description of our structure. And on the other side, since we, for this case, work with a XILINX evaluation board, we go to XILINX, Vivado, or Vitis, and configure our DPU core. So DPU is the abbreviation for Deep Learning Processor Unit, and this is an IP acceleration core for XILINX FPGAs. And this is configured here, and then we can combine those two parts. So we take our network, we do some quantization on the network, and then we take our DPU configuration and compile the network in such a way that it can be understood by the DPU core. So this is mainly this output here, this .elf file here. And then we can go into our application, so we can write our code and have a Peter Linux operation system with which we can finally cross-compile our application for our target application. So this is the main workflow we used here in order to bring a network structure onto, in this case, a specific XILINX evaluation board. Of course, this workflow changes if you change your target platform, or if you go to another technology there. Okay, so now finally some experimental results. So as I said initially, I would like to show you some results for an object detection task where we tried to detect our company logo, which you see here on the right side, at different scales, orientations, backgrounds, and so on. So we had to distinguish, in this case, two classes. So we have a logo class and we have a background class. And for that, we captured some images here, split this up into a training and a validation set. Here, just some words on the model we use. So I said this initially, we used the mobile net structure for feature extraction and the localization. We used the SSD. So this is number of parameters we had in the end after designing the network were about 880,000 parameters within the network. And then we applied our training and pruning concept. So we had 3 phases. We started with a short training phase. Then we introduced the pruning in order to compress the network structure, and finally had some fine tuning in order to compensate for the accuracy drop. And as you can see here, we were able to reduce the number of parameters at about 12%. So after pruning, we only have 770,000 parameters left, which should achieve a similar accuracy as the unpruned network. And that's what you see here within this image. So this is just one test image where we try to detect our logo. So you see here 4 logos which should be detected by the network, and you see the result for the trained network on the left and for the pruned network on the right, and you see both networks were able to convincingly find all 4 logos within the test image. And now finally some performance evaluation on the target platform. So therefore we had 2 different GPU configurations, so one with 512 operations per clock cycle, one with 4096 operations per clock cycle. So you see a factor of 8 between those 2 configurations, and in the ideal case we would also see this factor of 8 in the inference time on the target platform. That was not the case, so we saw here a factor of about 4.5 between those 2 GPU configurations. And finally, a comparison between the trained and the pruned network for this larger GPU configuration here. As I said initially, by pruning, we were able to reduce 12% of parameters. And again, in the ideal case, we would also see those 12% in the inference time at the end, and this was not the case. So we had about a reduction in inference time of about 7%, which we achieved by the pruning. We saw that a reduction in number of parameters does not necessarily result in a reduction in inference time. Okay, so finally, in order to sum this up, that's what I said at the end of the last slide. Again, we saw that, or we said that for us, pruning should be as flexible as possible. We did not want to consider this as some black box scenario, but we integrated this into our internal workflow. And for us, some kind of future work is to use profiling techniques on the target platform itself in order to control the network design or choose a proper network. Okay, so finally, last summary and outlook. So I talked a little bit about the Solectrix workflow for implementing AI in an embedded project. I talked about network selection, some pruning methods you could use. We integrated all those parts into a company internal tool, which we call the ecosystem. I showed one example workflow for bringing those structures onto a target platform and had some experimental results for the logo detection. And our future work includes, but of course is not limited to optimizing the model structure based on doing some profiling on the target platform. That's what I already said. And of course, also depending on the project, transferring those workflows to other target platforms. Okay, so that's all from my side. Thank you very much for your attention. And of course, if you have any questions, feel free to ask, and hopefully I can answer them.